I'm going to pause. It'll feel like I come right back to you guys. Okay, back from being paused. Talking about diffusion. Mass transfer happens atom by atom, ion by ion. And it can happen in three different ways. We can have grain boundary diffusion, volume diffusion, and pressure solution. And we'll look at each of those individually. So, well, almost individually, because grain boundary diffusion and volume diffusion are very, very similar. It's the same mechanism. The only difference is whether it's happening along the edge of the grain or through the body of the grain. So you can see in this little diagram, the one set of arrows is just showing movement along the boundary, and the other is showing movement through the body. Both versions of this require high temperature. Without the high temperature, there isn't enough energy for the movement of the atoms and ions through the material, because this is through a solid. In this, there also have to be the vacancies, the point defects. The vacancies move towards the high stress, towards sigma 1, and the ions move to the low stress, towards sigma 3. This is also referred to as solid state diffusion. Now, even though it's easy to think of void spaces like air pockets, it's not the same thing, because if you have like a balloon filled with an air pocket and you apply pressure, the air moves towards the low stress, the sigma 3. This is void space. There isn't even air in it. It is a gap in the atomic structure. So the material, the atoms, the ions, move away from sigma 1 towards sigma 3, and the voids go towards sigma 1. And you can see the type of distortion that can happen, where as they move away from sigma 1, the grain gets narrower and it extends in the direction of sigma 3. It can even change from, in this case, like a pentagonal shape to a hexagonal shape. But the total mass stays the same. In pressure solution, you have lower temperatures, but you have fluid. The fluid is vital for pressure solution. The name kind of implies that you have high pressure and you have a solution, you have fluid. This one only happens on grain boundaries, where the fluid and the mineral can interact. It can look visually the same as the grain boundary diffusion, where things move along the edge of the grain and the final result is the same shape. But if you have pressure solution, again, it can happen at much lower temperatures. This is fluid-assisted diffusion. The reason it can only happen on the grain boundaries, though, is that the fluid can't interact with the inside of the mineral grain. Therefore, only where it can actually dissolve into the fluid and then redeposit is where you'll have this kind of diffusion. Recrystallization occurs to relieve remaining stress. Recrystallized crystals do not show any deformation like the surrounding crystals. So the ones that have that solid state diffusion or fluid assisted diffusion, they'll show distortion, they'll show differences in atomic arrangement that can show up when you're looking, for example, in cross polars. However, a recrystallized grain isn't going to show any distortion. It'll look like it grew that way, because it did. It just grew that way afterwards. Now, recovery is another way that the crystal relieves its internal stress. The bonds from those dislocations recover and go back to normal. To accomplish this, vacancies must make it all the way to the edge of the crystal. Once they do that, then there are no more irregular bent bonds. So this happens, of course, when you have a differential stress, so sigma 1 is much greater than sigma 3. You have diffusion going on, and those vacancies make it all the way to the edge. Then a lot of that internal strain and stress has been relieved, and the crystal is apparently a tiny bit tinier. If you could measure it, it would be smaller by 1 ion, but the mass hasn't changed because all you've lost is a vacancy. Now, the moving of these dislocations can either move to a wall and seemingly vanish, or it can move into a cluster, and then that cluster can migrate. Superplastic creep is movement by distortion, grain boundary diffusion, and sliding past each other. So each of the grains changes shape slightly and slides along the grain boundaries. You can see here hexagonal shapes of each crystal. During an intermediate stage, they're distorted. They're still hexagonal, but they're irregular shaped, and 2 of them are actually hexagonal, 2 are pentagonal. The final result is all the crystals are back to hexagons, like they should be for a hexagonal mineral anyways, but they're oriented differently. They're turned by 60 degrees, except they didn't rotate. They got smushed. You can see down in diagram B here, where you have points moving over to new locations by diffusion. So, in summary, ductile deformation is permanent, so it's not like elastic deformation. You can see atoms or crystals or grains moving through numerous methods that we talked about. Plus, you can look in the book on table 9.6, page 234, for a complete list. And sometimes the deformation isn't obvious until you look under a microscope, where you can see the mechanical twinning that may have taken place.